Okay, so this chapter, the title of the chapter, as you can see, is Static Equilibrium and Elasticity. These are sort of two different topics, and they seem unrelated, but in a lot of structures that we build, they both come in play. Okay, so that's why they're lumped together. And anyway, what you'll see is the first part of the chapter is based on two equations, and just based on those two equations, you will do an entire course in your junior or senior level as engineers called statics. So this is an important topic. So let me set this up for you guys. All right, so now, okay, everything we've been talking so far, we've been treating what we don't explicitly state it, but we've been dealing with large objects, but we've been treating these large objects as a point object. And what was not said was that was because we assumed that all forces were applied that went through the center of mass of the object. Okay, so anyway, we kept things simple. Every point on the object had the same velocity, same acceleration, and so we were able to treat the object as a point object. Okay, now we'll graduate from that, and we'll actually treat objects as extended objects. Okay, so let's set that up. All right, so let's say we apply, okay, let's go back to a point object. And let's say I apply a force of 10 newtons in this direction. Okay, and I apply a 10 Newton force in this direction. Okay, and now obviously the sum of these two forces is 0. So if this object was the net force in this object is 0, and if it was at rest, it'll remain at rest. Okay, we all know that. All right, so let's try and do the same thing to this extended object. So we'll apply a 10 Newton force here and a 10 Newton force here. Okay, now this object will remain at rest. Okay, just like the point object, just like this object will remain at rest as well. Now let's do something different. Okay, so we'll take the same extended object. Okay. Now we'll apply a force of 10 newtons here, okay, and 10 newtons here. Okay, so just like for the point object, and just like in this case, we're applying 10 newtons to two 10 Newton forces to this object, except that this time now we're applying the forces at different points of the object. Now, if you were dealing with a point object, there was no issues like that, because all you have to do is all you can do is apply the force at on the point. But here, now we have applied these two forces at different sites, and now you'll find that this object will not remain at rest. What will happen instead is this object will rotate. Okay. So all this can be summarized by stating the following. Okay, so for point objects, the only condition you need for equilibrium is the sum of the forces be 0. And you can see that here for an extended object, the condition that the sum of the forces be 0 is not sufficient. You see that the sum of these two forces is 0, but this object is not in static equilibrium, it is rotating. Okay, so you find that a second condition is needed, that the sum of the torques be 0 for extended objects to be in equilibrium. Okay, And these two equations are the basis, are the foundation for an entire course that you'll be studying in senior level classes called statics. Okay, and that is what we'll cover in the first part of this chapter. Okay, so again, the first part of the chapter is about studying equilibriums of extended objects, and you find that you need two conditions to ensure that this an extended object is in equilibrium: that the sum of all the forces acting on the object be zero, and the sum of the torques of these forces. Each of these forces has a torque, and the sum of the torques need to be zero as well. In this diagram, both conditions are satisfied. In this diagram, this second condition is not satisfied. The sum of the torques is non-zero, and so this won't be in equilibrium. In this case, since both are zero, this object will be in equilibrium. All right, so that's the first part of the chapter. Let me tell you what I'm going to talk about in the second part of the chapter. So let me go to an appropriate slide. Let's see. No. Okay, here we go. All right, so in the second part of the chapter, we will encounter the following situations. Let's say here is an object, and we'll apply a tensile force on it. A tensile force just means a force that will increase the length of the object. Okay, a compressive force would be a force that would decrease the length of the object, and a compressive force would be applied in that direction. Okay, so that would be a compressive force. Anyway, those are just terms. Okay, so we are applying a tensile force, and what you can see is, so even if this was a steel beam or a concrete beam or whatever, you apply force and the object's dimension changes. So the length of the object increased. Okay, and what we want is, we'll encounter situations where what we want is when you let go of this force, when you eliminate this force, what we want is the object to go back to its original shape. Okay, and that is the subject of elasticity. So if the object goes back to its original shape, then the object is exhibiting elastic behavior. Okay, so what we want is to study under what conditions will this object behave elastically. So you can imagine that you can apply a great enough force where the object deforms permanently, or even cracks, or its structure is compromised. Okay, so what we want to study is under what limits will the object behave elastically. All right, now let's see. So let's talk about this a little further. Now let's say we apply 1,000 Newton force on this object. Imagine that this is a steel beam. What you'll find is you applied 1,000 Newton force, and this object stretched a little, extended its dimension, its length increased a little, and then it stopped. Okay, so the question is, why did it stop? So here's an atomic model of this object. Okay, so imagine that's the direction in which it's the length, that's the direction of the length of the object. So there we go. And we applied a force on it, 1,000 Newton force on it. Okay, 1,000 Newton force on it, and this object stretched about that much and stopped. So what happened? So at the atomic level, here's what happened. When you applied this force, each of these springs stretched. So the solid is modeled by atoms in these locations, and you can imagine a spring force between them. The forces between the atoms is modeled by springs. Okay, so when you stretched on it, each of these little springs got stretched, okay? And those were pulling back on those atoms. And all those pullbacks added up to the 1,000 newtons, okay? So the more they're stretched, the harder they pull back, okay? So the harder you pull, the more you will stretch. The harder you pull, the more you'll stretch these springs, okay? All right, and the more the springs are stretched, the greater the increase in length. So what we're saying is the structure will stretch, deform till the point where the internal forces balance the external forces, and that's how much it'll deform. Okay, and as long as the force is not too great and the internal forces are able to balance the external force, the structure won't be compromised. Okay, so that's what's happening at the atomic level. Okay, now let's look at an application. So we are interested in this kind of stuff for the following reason. So let's say here's a bridge, and you have vehicles going over the bridge, and every time a load on the bridge increases, see these cables supporting the bridge stretch, okay? And these cables holding the bridge stretch. And after the load is gone, after the vehicles are gone, what you want is you want to make sure that the cable goes back to its original shape. So you want all these cables to exhibit elastic behavior. If, on the other hand, if the cable's permanently deformed, pretty soon your bridge will be deformed. And how many times do you want the cable going back to its original shape? Millions and millions of times. Okay, so you are interested in structures exhibiting elastic behavior in some of the things that you build. All right, so those are the two things we'll study and we'll look at in this chapter. Okay. Okay, so what I'll do is I'll pause the recording, and I will give you a chance to